questions? All right. Okay. Dave says start system Verilog from basics. It is confusing. What exactly is confusing there? What have you not understood? Anything that you want me to explain again? It gets mixed with C and Verilog. Okay. See, don't worry so much about constructs. Okay. You should not worry so much about syntax. That is always available for you to go and refer, right? That I have referred you to that manual, right? This manual has a lot of examples, etc. Right? See, you don't have to worry so much about the syntax. You can always go and look it up. Even I don't remember. You have to understand the basic ideas. If you have any difficulty in any of the things that I discussed yesterday, let me know. For example, we talked about very simple things like strings. We talked about various data types, right? Among them, if anything is not clear, let me know.
Sir,
We talked about, yes.
um, for design, we only use Verilog or we use System Verilog, and then for verification, we use System Verilog. Is that right?
For verification, we use system. System
But the
Verilog
design is
is
still
not used for synthesis.
okay. Okay.
Yeah, system Verilog is see the kind of constructs that are there in system Verilog, they cannot be synthesized. Okay, they are mainly for making test benches. All right.
One more thing, sir. In the current scenario, is still System Verilog the most popular and the best for verification, or is there any other software,
No, system
any other
Verilog
language?
plus UVM. See, there is something called as universal verification methodology, which is built on top of this system Verilog. So industry
Okay, sir.
uses system Verilog with UVM.
Okay, sir.
So it continues to be the most popular. Okay. All right. Let us take maybe an example. Okay. So imagine that we have to add um, two. There are two registers A and B, and let us assume that they are either 16-bit. Okay, let us assume that they're 16. They contain BCD coded or binary coded decimal. So for example, A may contain 4567, and B may contain 6593. Our objective is to add them. So 7 plus 3 is 10, so 0. 7 plus 3 is 10. Carry 1. 6 plus 9 is 15. 15 plus 1 is 16. Then 1 plus 5 is 6. 6 plus 5 is 11. Then 1 plus 5 is 1 plus 4 is 5. 5 plus 6 is 11. And there is a carry. So the answer is 1160. And there is a carry. So we have to perform this. Okay, we have a 16-bit register containing A. Okay, this number, and A contains this, B contains this, and at the end we would like a register called C which contains this. Okay, this is a BCD pattern. Add, I don't know why it's so bad here. Add two 4-digit BCD numbers. That is the idea. So any thoughts on this?
Or we can use binary adders, 4-bit binary adders, along with some correction
Hmm.
circuit for change, moving out of the relevant BCD code.
Hmm, hmm, hmm. That's right. Correct. So that is definitely correct. Let me just complicate it a little bit and assume that these are A could be 64 also. A can be anywhere. So A can be 16-bit, 32-bit, 64-bit. Okay, it's up to us. We can decide the size of the BCD numbers that we are adding. So if we have 64-bit, we have 8 digits, no 16-digit BCD. So it's a long BCD number of up to 16 digits. So how does it? What will be your solution if I say that it can have as many as uh, 15? So how do you think we can do this? Any doubts? I'm sorry, any ideas? So let's try this exercise. What are some building blocks? So we need to start with some building blocks. What would be a building block?
One should be adder,
Adder? What kind of adder?
binary adder,
Okay. How big?
4-bit blockwise.
Okay. Why are you saying we should use a binary adder? We are trying to add BCD numbers, right? Why are you saying that we should add a binary adder?
Yeah, but BCD adder is usually implemented by using binary adders, 4-bit binary adders for each
Mhm.
digit.
Yeah, yeah. See, it's better to say we will use a BCD adder, right? So that is the
Yeah,
right
yeah,
answer, right?
yeah,
The
yeah.
module BCD adder. So what are the inputs and outputs?
A and B are the input.
Correct. No, if you say A and B, you should also tell me what is the size of the inputs, right? So A and B are inputs, I agree. So maybe
0
this
to
is
VT.
A in and B in, and the output is maybe, and we also may need a carry in, and we'll need a sum out and carry out, right? And we should write a statement somewhere that A in is a BCD digit.
हेलो भाई, तेरे सामने वाली खिड़की से चांद का टुकड़ा है।
All participants, please keep yourself muted.
और क्या भाई, चाय तो यार मैं पी के ही आया तो यार, कल घर जा रहा है। अरे अभी क्या घर गए तो फिर से घर जा रहे हो? ठीक है,
Okay.
मैं क्या कर रहा हूँ बता।
Now, what is A in and B in? They are both inputs, right? Now here we have a choice. If you want, we can call it logic, input logic, 3:0. Similarly, output logic 3:0 S out. And we could say input C in and output C out. Again, we can say input logic. Okay. So make sure that this actually is accepted. Okay. I want to make sure because I don't know, sometimes your IKRS may suddenly come back and say that not all system Verilog constructs are still understood by IKRS. Yeah, IKRS is a free tool, so it is still not fully compatible to system Verilog. Right? So we have described the inputs and outputs. Okay. Anybody remembers what logic meant? What is logic?
Only 0 and 1.
No, no. Logic is actually, it can take 0, 1, X, and Z. Okay. It is a four-state variable, right? Bit, on the other hand, is two-state, 0 and 1. Okay. So logic
Okay,
is
sir.
0, 1, X, and Z.
But it can be either reg or a wire.
Huh?
It could be taken as reg or wire.
That's right. It can be taken. So if I assign to it, there will be no complaint. Okay. It doesn't need, I don't have to worry about saying it's a reg or anything like
Yes,
that.
sir.
Okay.
In
It can be
system
treated
Verilog,
as,
we can use logic in place of as we what did in the log, like wire or reg.
yes, yes. That's right. Now, how do we proceed? So we can say whenever any of the inputs change, okay, so we are welcome to use this at star so that we don't have to actually enumerate all the inputs, etc. It will figure out what are the inputs to which it is sensitive because we are going to use those inputs in our always statements. We'll be writing statements. Right? So we could say A in plus B in plus C in. So we'll add these three, right? And that will result in, let us say, a temporary variable, okay, which is a logic. So we added them as binary numbers. So this is the ordinary binary addition. This plus means binary addition. So what can happen when we add binary numbers is so imagine that I think we took some example earlier. If 4 plus 5, 9 is a valid BCD. On the other hand, 5 plus 9 is 14, right? So there is a sort of a problem here, right? 5 is what? 0, 1, 0, 1. And 9 is 1, 0, 0. So it will come back and give 1, 1, 1, 0. Right? So this is incorrect answer. What we need is 4. Okay. So what do? We have to correct the answer. Okay. So this is actually right now E, right? Whereas the correct answer is 1, 4. Okay. The correct answer is 1, 4. So 1, 4 in hexadecimal is 20 and E in hexadecimal is 14. So the correction involves adding 6. So if we find that 5 plus 9 resulted in an incorrect BCD number, right? So we will go and add 6. Okay. So that will cause a 14 and we will get a carry. So 1 plus 4, 5. 5 plus 6 is 11. See, 11 is also, unfortunately, it is a, in binary, we will have 1011. Okay. So 1011 will become A. A is 10. But what we really need is 11, which is 17. Okay, 11 in hexadecimal is 17. 14, 1 plus 6, 7, 7 plus 4 is 11. So 11 is 17. And right now we have 11. So the difference is 6. So again, we have to add 6 here. So the better way to understand this could be we have 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0, 1, and 0, 1, 0, 0. So this we are adding 0, 1, 0, 1, then 1, 0, 0, 1, then 0, 1, 0, 0, and 0, 0, 1. So when you added these two guys, we got 1, 0, 0, which is a valid BCD digit, so no problem. When you added these two guys, you got 1, 1, 1, 0, which is unfortunately not a BCD digit. So we are saying add 6. That will cause a carry to come here. So the corrected value here is 4. and this value is already 9. It's correct value. Now when you add, you get 101. 1011 is not a valid BCD. So we have to add 6. So that will result in a 0, 1 here and a carry here. So now we have 7 plus 2, 9, 9 plus 1, 10. So I'll get 1010. Once again, we have to add 6. So that will make it 0, 0, 0, 0, and there is a carry. So the actual answer will be 4 plus 5, 9, 5 plus 9, 14, 7 plus 4, 11, 8 plus 2, 10, and carry. So the 0149 is what we will have. Okay, so that is what we have to implement. Okay. So what is the condition for me to add 6? Okay, under what conditions should I add 6? Okay. I should definitely add 6 if the resulting value is not BCD. Okay. If the resulting value is not BCD, I should add 6.
Also, if the nibble generate a carry.
Yeah. So in case, let us say we had a situation where a carry resulted. Let us take maybe 9 plus 9. When I add 9 plus 9, what will happen is we'll get 18. Okay. 18 will result in a valid BCD number here. So we'll get 0010 here, and there will be a carry as well. So the carry will be here. See, this is also incorrect. Okay, we have to add 6 to correct the number. So that is what we have to do. So we have to check if we either have an invalid BCD digit, or if if there is a carry. So if temp is greater than 9, right? Maybe we can call it temp sum and temp carry if you want. So if temp sum is greater than 9, or temp carry is equal to 1, I think it may be okay to just call it as one sum and say greater than 9. See, that may also be. We can call it as a 4-bit 5-bit number, and if that 5-bit number is greater than 9, I think we have we have to add. Mhm. If temp sum is greater than 9, then temp sum equals temp sum plus 6. And what is the output? The output is nothing but the last 3 bits of temp sum, and um, we can say assign S out equals temp sum B to 0 and assign C out equals temp sum. So we don't know. I'm assuming that this is correct logic. Okay, so I'm just keeping a little suspense to see whether this also will work. Yeah, if you know it's already correct, then verification is little bit not very useful. We are still not very sure whether it will work. So compile this and make sure that it is accepted. Okay. Now first let us verify that this guy works. This BCD digit will work. So module digit adder test. So let us add this input logic 3 to 0. Let us say X and let us pretend this to be 3:0. Similarly, logic 3:0, Y 3:0. This means X and Y are arrays of BCD digits. We can keep it higher also. We can keep it maybe, whatever, 7 or whatever, 8, 10. Then logic 3:0, Z is also set 10. Then we can have logic for carrier. Initial begin. Let us connect we'll create another logic 3:0, A, B. So this is A, B, and so what we'll do is where is that BCD adder? BCD adder, right? So A in we will connect A, B in we will connect B, C in we will name it right. I think we need one more logic. So we have tried everything. So in the initial part, we'll initialize X and Y. Yeah. For integer I. See, in a system Verilog, you can declare integers inside initial block, etc. In Verilog, you can't do all that. So you have to declare all the variables, here. But system Verilog gives a little bit flexibility. It allows you to put int I, etc. Like C language. For I equals 0, I less than or equal to 10, I plus plus. So initialize x and y. So x of I equals, let us say, u random range 0 to 9. So it gets some arbitrary digit, BCD digit. These are my inputs. Okay, I have some 11 BCD digits. Hopefully, they'll all be sufficiently random. And we can copy A to x of I and B to y of I. Only we need not have, these are a bit redundant. X and Y, we can do it directly also. We need not first assign to X and then assign to Y. So this is a little bit redundant. Directly we can assign it to Y. Then Cn is U random range 0 and so we have put some values on A and B and Cn, and the output will be sitting in Z and carry out. Right? We wait for 1 unit of delay and then display A equals percentage D, B equals percentage D, C out equals percentage D, and Z equals percentage. And A, B, C out, and Z. I think we have to display C in also. Correct? So this number can be any value, 20 also. So we are trying 20 test cases. So 3 plus 5, 8 plus 0 is 8. 8 plus 1, 9 plus 8 plus 8, 16. 16 plus 1 is 17. 7 plus 1, 8. 7 plus 2, 9. 9 plus 1 is 10. Okay. So what would be a way to automatically check? Okay. Instead of going through all the display values, can we write a way? Can we write a statement which checks whether the error is there or it's correct.
Or you can add them as integers.
Yes. So we could say if a plus b plus c in equals, what should you what will you write? See, the C out has a weight of 10 and Z has a so if this is true, then everything is fine, right? If this is not true, there is some problem.
Yes, sir.
Okay. So when we run this, hopefully we'll not get any error. So all the cases were run, okay, and we did not have any error, right? We are not sure whether all the cases were there. See, we are not sure whether the temp sum that carry situation did it occur, or whether it's only happening because of the right, that we are not sure. So if you want to print that temp sum, you are actually allowed to print. So we could say display temp sum and you can say this instance name bcd add inst. In that we want temp sum. So let us see how that has gone, whether it was all the cases were generated or not. So looks like you can see that in some cases it is 1, some cases it is 0. So it looks like all those cases were generated. So our confidence is higher now because it's not just see, because when we do random testing, we worry that maybe some cases were never tested. If there is a bug in that BCD adder logic, then we will not be able to expose it if certain cases didn't occur. Okay. All right. So now our problem was to design a larger BCD adder. Okay. So we wanted a module called BCD adder, let us say n bit, n digit. So what are the inputs to this guy? We have to have A in, B in, C in, and we will also need some of carry. It is almost identical. The only difference is the register A in is much larger. Okay, so the input logic. So how big is this? we may want to say something like 4 times n. Okay, because each BCD digit takes 4 bits. So as a result, we need 4 n bits to store A in and B. And similarly, output logic 4 times n minus 1 to 0 sum output. And Cin and Cn out are 1 bit logic. You can see that the availability of this logic really helps. And here we may have to say input logic. So the advantage of this logic is we don't have to say whether it is a register or a wire. Do you think we can see one way is to use combinational logic? Okay. But see, we will need too much. We'll need many BCD adders, number one. And if you ripple that, so imagine that we are doing something like this, right? We have many BCD adders, one digit BCD adders. And we are sort of creating a ripple effect. Mm. So this carry output will have to wait until this carry becomes available, which we has to wait until this guy has to become available. So the delay here may be very large. So this is one reason why we may want to avoid something like this. Okay. So we can, in one extreme case, we can use a single BCD adder. And what we can do is, so we have two registers. We load the BCD numbers into the registers. These we will give as inputs to the BCD adder. So this is my A register, this is my B register, and this is my C register. So we'll add A naught plus B naught and put it in this last position. And then the carry will be remembered. Okay. So the carry will have to be remembered. and this carry is the one which we feed back. Initially, the carry is loaded here. So this is a 1-bit register. In this Cin, we load a 1-bit value, that's the input carry. This input carry that we have here. That we load here. And in the next cycle, the output carry will be loaded and things like that, right? And then having added A and A naught and B naught, one thing we can do is we can do a right shift or something like that. Right? So next A1 and B1 will get added, right? And here also we can right shift, and the new value will get stored here. And if you repeat this, then ultimately the values will all get added and get stored in. So it is like a reuse of this resource. Okay, we are using the same resource. So this is an extreme case, whereas here we have all everything is combinational. So it has more hardware. So ideally, it should give us a lot of advantage because we have a lot of hardware. But then this carry output may become very slow. So that is when we have to consider maybe an alternate. Okay.
So can we say the
So
second one is an RTL design?
what?
Can we say the second design as an RTL design, RTL architecture,
RTL? What?
a register transfer level design?
Yeah, these are all RTL. Yeah, right. So we'll declare a register called logic 4n minus 1 A in B in, not A reg B reg, and there is a 1-bit logic called C reg. And we will need clock and reset because this is a sequential circuit now. So we'll need a clock and a reset, right? So we have added the registers. So now we can possibly go and describe what happens when there is a positive edge of clock or positive edge of reset, right? So since this is system Verilog, we can add all this so that it is easy for somebody who reads the code to understand. So if the reset has been pushed, then what could we do? We could possibly load the registers. A reg must be loaded with A in, B reg must be loaded with B in, and C reg must be loaded with C in. We just loaded everything. And maybe some reg we can initialize to 0 or something like that. We need a sum reg also. We will initialize the sum to all zeros, right? And maybe we need a counter. We need to track how many times we need to do this, right? So the number of times is 8 only, right? So we need a counter which is initialized to maybe n, right? So how big is that counter? It should be able to accommodate n.
Three bit.
So we need at least one extra, right? So 1 plus $C log 2 of n, right? So if it is 8 bits, see, we'll have to check for 1000. Okay, so we may need one extra. Okay, count. And that count also has to be initialized to 0. If this is not the case, that means if it is not a reset, then that means we are receiving the clocks. So what we have to do is we have to initialize that BCD adder here. That instantiation we have not done. So it is BCD adder. So we need one copy of the BCD adder here. And the instance name we can give whatever last digit LSD adder. It adds a last digit. And here what we have to do is maybe A 3:0 and B 3:0. Right? The last 3 bits of A will come in here. And C in will be C reg. And this will be S reg 3:0. Let us do one thing. Let us keep logic 3:0 sum and carry. We'll take the values into this. Maybe we can call it BCD sum and BCD carry. Correct? So when the clock comes, remember the data is already available to the combinational logic. So when clock comes, already the addition is ready. Okay. So all the clock has to do is to load sum reg 4n minus 1 to 4n minus 3 minus 4, I think. 4n minus 1, 4n minus 2, 4n minus 3, 4n minus 4. Those are the last 4 bits. And then that must be loaded with BCD sum. And then C reg must be loaded with BCD carry. And once that has been done, we can shift everything. So how do we shift? We can say A reg shift by 4 bits, B reg shift right by 4 bits. I think it is like this.
Sir, in line T, should we not use a variable instead of capital N?
What?
In line number 50, 50,
Hmm. Hmm.
should we not use a variable instead of capital N?
Instead of capital S.
Capital N.
That is N, no? That N is the parameter. N is a parameter. See, sum ridge is 4n minus 1. Okay. This should be 4n minus 1 to 0. So it is a 4n minus 1 to 0. So the last 4 bits we are loading. Is that clear?
So are we going to repeat this multiple times?
Yeah,
Thi-
it
This,
is automatically getting repeated. No, every time the clock comes, it's happening, and the count will be count minus 1. So we are decrementing the counter. I'm sorry, count should be count plus 1 maybe, or maybe we can load it with n and count equal to count minus 1. So every time the clock comes, it's this whole thing is getting repeated, and we should actually stop doing it when count becomes 0. We should stop doing it when the count becomes 0. So one way of doing that is we can give an external signal, right? Called complete or finish or whatever. So finish is a output logic. So once again, what we have done is we have done something like this. We are drawing. So we have two registers A and B. This is A reg and B reg. This is 0 to 4n minus 1. So for example, if it is 8 BCD digits, we will have 32 bits. So initially, we load this from that input that is given to us. I think we have called it as A in, and we have called this as B in. And we have a 1-bit register called C reg. And we load that C in here. We take these last 4 bits and this guy, and we'll connect it to a BCD.
sir, we should also shift the sum output also, isn't it?
Yeah, we are shifting, no? So there is a sum register. So this guy is coming here, the last 4 bits. And the carry that it provides is also sent back. So ideally, in a real hardware, we may have a multiplexer, right? And depending on whether we are doing in the beginning, if the reset is true, this will get you know loaded in C register. Otherwise, it will the feedback from here will get loaded. So C out, and this is C in. So when the reset comes, there is a count here which will initialize to n. Let us say the input is 4, 5, 6, 7, 8, 1, 2, 3. And this is 2, 1, 8, 3, 4, 5, 6, 9. So this 3 will be in A register in the last position here. And 9 will be here. And let us say carry was initially 0. Let us say we are interested in adding 0. So the 0 will be sitting here. So 0 plus 3 plus 9. Our BCD adder will provide 2 as the output. And there will be a carry out, which will get loaded into this. And everybody will shift. So this will go away. We'll get possibly zeros on the left hand side. And some also, the 2 will get shifted and we'll get 2 will go here. And next time when the clock comes, this is repeated. And every time we are subtracting n minus 1, etc. Finally, it will become 0. Okay. After that, if the, ideally the clock should not come after that. The person who uses this should know that the output should be collected after the finish is obtained. So it doesn't matter what you do. Okay, you can continue to do something. It will possibly continue to do addition of zeros, right? Or you can even check whether if finish is not high, then do something like that. But I think it is okay to just let it go. Okay. So the outputs that we have to generate are sum out. So that is nothing but sum register. Okay. So we can say output is nothing but S out, sum out is nothing but sum register. Then C out is nothing but the C out of that BCD. I'm sorry, BCD carry. And the finish, okay. See, we have done if count becomes 0. So one way to say it is assign finish equals count equal to 0. So the test bench should wait until finish is 0 and keep on supplying pulses. So this is a RTL design. This is a tester for the first module, so we can go ahead and maybe we have already tested it. Now what we want to do is we want to test the module BCD let us say 32, 32 tests. So to use this, we will need a clock. We'll need a reset. We'll need maybe a 31 to 0 of A and B. And we'll need one logic scene and logic CO. And sum is also a C. So they are all logic. So hopefully we have everything to go. So now we initialize BCD adder n with n equal to 32. Oh, sorry, n equal to 8. 8 n there refers to the size of the number of digits. It doesn't refer to the size of the. So here also maybe we should call it BCD 8. We send the clock reset A, E, C in, then sum, then C out. And we also need that finish. Okay. Then we should initialize maybe the A and the B registers. Initially clock is 0, reset is 0, A is we have to create a random BCD digit. See, that is not going to be easy. Okay, we can't use U random range like that because each digit may not be BCD. So we may have to create a loop. So int I for I equal to 0, I less than n, I plus plus. So what I should write here is when what will be the range? The BCD digit 0 will be between 0 and 3. 1 will be between 4 and 7. So 4 times I, so 4 times I minus 3 or something like that. So when I is 0, you can see that it will go from 0 to 3. When I is 1, it will go from 1 to 7. And then finally, when we get n minus 1, it will go from 4 times n minus 1 or 4n minus 4 to 4n minus 1. And similarly, B. So even creating random data takes time. We have reset, we have added some data. Now we have to reset by sending a pulse on reset. Then let us repeat 10 times or 8 times. So this should be 8. No? Repeat 8 times. So first set clock equal to 1 and then set clock equal to 0. Okay. So we are going to send 8 clock pulses because this is 8 times. Right? And here we can display the values. We can display some. Maybe here we can display on A and B. See, let us do percentage H. Okay. And B also percentage H. Right? And C in is percentage B. And A, B, and C. Okay. And here let us display sum also as percentage, or maybe we can display all the registers. A will not help. A or B is displayed. Sum is the only thing that makes sense. Sum and COT. Okay. So we'll try it out. See, we added N. So I think we forgot to. This is always a problem. It is 34. Design at 23. No, we have forgotten to display there. So that is that problem. If this is a problem. Okay. It is not allowing me to write an expression. So the only way I can do it is 3 to 0, and then we can shift to. So we keep shifting so that we can create. It doesn't allow expressions in this. So our numbers are A is this and B is this. Okay, so looks like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So both are 8 digits. Okay. Seen is exam. What I see. Yes. Mm. Sum out is, am I assigning correctly? Sum out is sum range, correct? How come it didn't complain here? See, that is what interests. It didn't complain at all. I gave an expression here. Maybe parameters are allowed, but variables are not. Okay, what do you think is a mistake? How do you debug this? We are resetting every time, are we? No, we are not doing that. No. See, this repeat is here. See, initial, then repeat is later. No? Clocks. See, initially we repeat, we reset, then we are doing the clock. Clock is initially 0. Reset is 0. We reset 1 and then back to 0. Then clocks are being done here. We are not resetting again. We'll just display A edge, B edge, and some edge. So A edge is present in that BCD adder n inst. BCD adder n inst dot A edge. BCD adder n dot n inst dot B edge. And then finally BCD adder n inst dot sum. So we'll see what is going on there. So initially average was loaded with this value. Then it is shifting correctly. Can you see? It's shifting correctly. It's also shifting correctly. But the sum is not going very well. The sum is always 0. The LSD adder takes this guy and produces BCD sum. So maybe we'll. Are we loading BCD sum anywhere? Are we? We're loading it. We'll also display BCD sum. So go ahead. So 0 plus 0 is 0. 9 plus 3 is 12. And the carry is 1. So 10 plus 7 is 17. Carry is 1. 8 plus 6 is 14. Carry is 1. 6 plus 5 is 11. Carry is 1. 1 plus 1, 2. 2 plus 0 is 2. 5 plus 7 is 12. Carry is 1. It seems to be doing it right here. The BCD sum is okay, but it is not loaded correctly.
Sir, why Cout is not a single bit?
Now, why? What?
Cout is not a single bit. Why Cout is a multi-bit number
Where?
in the output?
You have to tell me the line number. I don't know where you're.
I mean, in the result that is displayed, Cout is shown as like 32 bit or something.
Maybe I have displayed it wrong. CCO. Logic. Am I displaying it correctly? Let us check. See, average is this, average is this, BCD sum is this, sum is this. See, I have made a mistake in the display now. See, sum is this, sum out equals percentage. I have made a mistake in display. So this Cout is now corrected. So 0 plus 0 carries 0. 9 plus 3, 12 carries 1 and so on. So that is okay. But BCD sum is not getting loaded.
Sir, clock is it ticking clock? Sir, the clock, is it ticking 0, 1, 0?
Which line number?
Sir, in the test bench, line 44, clock is always 1.
No, here it is becoming 0, right? Clock is 1, then clock. Otherwise, it will not even go to all the 8 clock cycles. Okay. It will just do 1. Let us see what it is called there. See, it's not loaded at all. So BCD sum is the order in which I have connected, correct? The
There is
BCD
a
adder.
variable n creating problem while displaying some wedge.
Just a second. With the BCD adder, how have I defined BCD sum? BCD sum is 3 equivalent 0 is correct. BCD sum the BCD sum is correct, but for some reason
So I feel the posage is not getting detected.
no man, it is something to do with your this what is it called? The assignment being non-blocking assignment. Okay, so non-blocking assignment is possible because as soon as we are not waiting now, we are immediately going ahead. That is the problem. See, we are if I change this to this, it will work. Because if I do this, it does. Let us say initially it had 0, right? Then it schedules this for you know it schedules this statement for simulation. Then without waiting, it will continue. And this is also this is a display, so it's okay. But the others are also all non-blocking. So it just completes without even doing it. So sum remains 0. So unfortunately, we have to convert this into a non-blocking assignment because we are also going to shift now. Mm. So it shifts old stuff. Okay, so that was the problem. Did everybody understand? What I can go through it again. But did you understand this overall architecture? Did everybody understand the overall architecture? It is a serial BCD adder. Okay. It does things serially. It is the A and B are they have 8 BCD digits. It adds only one BCD digit at a time. So it is hardware efficient. Okay. Only one BCD adder required. But as a result, it will require 8 clock cycles to complete. And what is the period of the clock cycle? Okay. It is decided by how fast the BCD adder is. So the BCD adder requires you to, if you go into the combinational logic of the BCD adder, it has a 4-bit adder. Okay, maybe a the 4-bit adder is a ripple carry adder that we have created. Plus, there is some logic to add 6, etc. So that will decide the time it takes for this guy to get ready. So the clock will be decided by this. So if you know this delay of the BCD adder, then that number multiplied by the number of clock cycles, that is what this guy is going to take. Okay. If you had done it directly like this will be a little bit faster. Okay. The delay of the carry here, the delay of the carry here, etc., etc. It won't be exactly 8 times the delay of each of them. Okay. So on an average, it will be faster. So in comparison, right, this may be a little bit more efficient because it takes less area and achieves a reasonable speed. Whether it will, what is the exact speed, etc., you will have to do, that is the, you have to do the design with actual gates, etc., and see. Okay. So that when people talk about architectural design, this is what they mean. Okay. See, I could have other architectures. I could have a BCD adder which adds 2 BCDs at the same time instead of one. I can specialize, I can specially design a adder here which adds 2 BCD digits at one time. In which case I will, sort of require only 4 clock cycles. So you may have to do some study, right, on how many BCD adders are you willing to put here, right? Are you going to put 1? Are you going to put 2? Are you going to put 3? And in the worst case, all 8. Okay? And then the clock frequency will, you have to plot. So the number of clock
Sir,
cycles here
one
will go like
question.
this. It will be 8
Sir,
here. Hello.
Sir, when do we decide whether we should have a control unit or not in the architecture?
Control unit will be required here because it is sequential, right? So we will need a control unit. It's a very simple control unit. It has to control this mux. Okay, when reset comes, it has to become 0. I'm sorry, it has to be loaded from CN. And during the rest of the time, it has to come from here. And maybe the counter has to be decremented. So the
So
counter
there are
is it's very simple.
but we don't have a separate FSM here, isn't it?
Huh?
We do not have a separate FSM to control the entire thing.
The counter is inside. So we need a very trivial, it takes the clock and the reset, right? And it generates, when reset is high, it will set this mux to 1. And when reset is low, it will change this to, load from here. and the count has to be decremented every time. So you can design that control unit. It will be very simple because only very little has to be controlled.
It's basically the reset signal itself is acting as a controller.
Yeah, it may be very trivial. Yeah.
Okay.
So you can plot, n as the, you can take n on the x-axis, okay, and design a 4-bit, let us say this is a 1-bit BCD adder. You have to design with actual gates and see what is the delay it gives, and as a result, what is the clock frequency you get, and how many clock cycles you take. Okay. The number of clock cycles will sort of go by, it will keep reducing. So when n equal to 2, it will reduce to 1/4, 4 clock cycles. When n is 4, it will reduce it to 2. And when n is 8, it will only reduce to 1. Okay. But I can't say the same thing that the delay of the BCD adder may not scale linearly in any way. Okay, that will depend on what gates are used inside, what is the load on the interconnect. Okay, that depends. So it is not very clear. It's not obvious that one is better than the other. So if somebody wants to look at which one will be better, they have to go into actual, analysis of the video. So to repeat, I load my 32-bit number into a register. Okay. Similarly, A and B are both loaded. C is also loaded in a 1-bit register. Then there is a BCD adder which adds the least significant 4 bits. That is this BCD digit. And the output of this gets loaded into the sum. And we have to do 8 clock pulses, right? And every clock we are shifting this data. So that shift by 4 has to happen in one go. See, when you shift the data by 4 bits, you should not shift it 1 bit at a time. Then you will not get any speed. That shift has to happen in one go. Okay. That is what only then this adder makes sense. Okay. Yeah. Similarly, this shift has to happen in one. Any doubts in this so far? Anybody has any doubts? How this
So
works?
why the counter require additional bit, not C login?
Why is the counter?
Plus C login.
Because 8, if I have to load the value 8, then I need to have 4 bits, right?
But with the 3-bit, we can have 8 different cases. No?
See, if you have only 3 bits, then you will have to start with 7. Okay. 7 to
Yeah, from
0, and
7
then
to
how? I don't know. I don't know how you will do it. We have to start with n and wait to go to 0, right? So all the values have to be represented. You start with 8 and wait for it to go to 0. So the register
okay.
must have the ability to store 8 and all the way up to 0.
Okay.
I don't know whether there is a way to reduce it to 3 bits. Right? There may be some other way. I don't know. Any other questions?
So why increasing the number of BCD adders will not increase the speed?
Why increasing the number of BCD adders will not decrease? See, what I am trying to say is the BCD adder logic, if you see what is there inside, first it has a binary adder, which is possibly ripple carry adder, or it could be carry look adder. We don't know how it is built. Plus, there is some, add 6, etc. So and similarly, when you extend it to 2-digit BCD adder, again, we don't know, what will be the delay. Okay, you have to actually do the layout and see, right? It's not easy to answer whether you understand, no? See, it's not like at the architectural level, you don't have enough information. You don't have anything to anything that you can say about the actual delays, etc. We can only make some sort of a guess. Does this make sense?
Yes,
I'm not saying that it will be totally, when I say it doesn't scale linearly, I'm not saying that it will be so unpredictable that, but it will be definitely some, we may find that something in between 1 and 4 may be better. You understand? So this is one extreme, and this is the other extreme. So this is fully combinational, and this is fully serial. So something in between maybe, might be better. And that we'll know only when we actually do the, we had to do the synthesis and we had to see the actual thing, then only we'll, okay, it's not easy. All right. So you can try doing that, such things you can try. So these will be good mini projects that you can do. Okay. Any questions before we move on? Repeat and for loop. What do you mean by repeat and for loop? Repeat is repeat. Okay, the syntax of repeat is it? See, here is a repeat loop. We are saying repeat whatever I am giving here these many times. In for loop, you will possibly write for. I could have written this as for loop also. There's nothing wrong. I could have declared another variable and written for j equal to 0, j less than 8. There's nothing wrong. The same thing. Any other questions? Anything that can you tell me why I did percentage h? Why not percentage d? When I displayed the number, why percentage h?
percent D means its decimal value which is the result
See, if you
0
do
to 9.
percentage d, it will take the entire number and try to display it as a d. So debugging will not be easy because we are adding BCD numbers, right? So we want every 4-bit to be separately displayed, and that hexadecimal display will do it. In this example, the digits will only be from 0 to 9. We will never have A, B, C, D, E, F. But percentages will allow me to see the BCD digits separately. So that is why I have done percentages. Is that clear? You may have to repeat this multiple times. See, this only has simulated one case, okay, and it is working as far as we can see. The sum of the two is correct. Okay, this sum is correct. We can remove that. See, this kind of a display and all we should remove at the end. We don't want this. So we can remove and we can see that it seems. See, this is a this is a design. We should not put display, etc. there. Okay. For debugging purpose, we had put, but we should definitely delete it. Okay. What happened here? Let me. Hmm. So these are the two numbers. And when we add this, I think this answer may be correct. Okay. But we may want to repeat this again with all zeros or all nines. So that I will leave that part to you. Okay, you have to write more test cases, right? And you have to figure out how to, generate more random test cases. This will only generate one of them. Okay, so let me share this with. So we were discussing various constructs, logic we have discussed, right? Enumeration is another data type. Okay, so this is an enumerated data type. So here, light 1 and light 2 are enumerated data types. So we are saying that light 1 can take red, yellow, or green. See, this is much more readable than light 1 can take 0, 1, or 2, and then we try to interpret 0, 1, and 2 as red, yellow, and green. Right? See, the other day when we were trying to do that cows and bulls, we said 0, 0 means cow, 1, 1 means bull. So instead of that, we could have written an enumerated data type. Okay. We could have written cow, comma, bull, comma, some other, where it is neither cow nor bull. Unknown. Okay. So that is where this enumerated data type helps. If you don't say anything else, Verilog is going to give 0, 1, and 2 as the internal codes. Okay. There is no magic here. It is just it knows how many values are there. So in this example, there are 3 values. So it will need 2 bits to store these values. And it might say 0, 0 is red, 0, 1 is yellow, and 1, 0 is green or something like that. Right? And I think it will allow you to choose them. Okay? For example, if you, for some reason, if you want idle XX, S1, S2 as the 4 states, right? You want this S2, S1 to be 0, 1, and you want S2 to be 1, 0. Okay, then you can force it. It will choose the remaining. Okay? It may give 1, 0 to this and 0, 0 to this. Okay, things like that. Okay. And the nice thing is you can, how do you use these variables? That you would have explained somewhere. See here, this is a enumerated data type. So colors is an enumerated data type, or rather it's a type. Colors is a type, type def. Okay, it can take these values. So later I can define a variable called C, which is of this type, and I can say C equal to green. No need to. It is not a string. You should not put double quotes here. It's green. It understands what green is. You can also say C equal to 1. Okay. See, this is not correct because you don't know, right? You don't know which is 0 or which is 1, etc. So this is not correct. So you are supposed to say C equal to green. The correct way to check is if C equal to green. If you have to make a check, then you are supposed to say C equal to green, right? But it may forgive you if you say this is 0, this is 1. So they are still, they may take it. Okay. But this is all not good. You should not do such things. You should say C equal to green. Again, don't do all this. Okay. It's not correct to do all this nonsense. And on that enumerated data type, you can, ask for which is the first one, which is the first entry, their last entry. I don't know when you will need such things, but they have provided. So that's a very simple data type. Then let us look at the there are two more dynamic arrays. Okay. Ending stuff is not easy. The dynamic arrays is page number 35. Something like 55. 35. So these are dynamic array. So you can take any data type, maybe bit or byte or any logic, whatever you want. And you will define the name of the array. And at this point of time, you don't know how big it is. So dynamic array means when we don't know the size of the array, we can leave it empty. So here is an example. This is a data type with 3:0. And he wants to create an array of these. He calls it nibble. Similarly, mem is an array of integers. At this time, we don't know how many there are. Later, when we come to know how big it is, we can use new to allocate storage. Okay, like here. At this point, we don't know how big the ADDR array is, but at some stage we realize that it should be 100. So we can say ADDR equal to new 100. Later, you may want to extend it to 200. When you say new 200, it may remove all the old stuff. You already had 100 elements. Okay. If you just say new 200, you can't guarantee what will be there in that stuff. But if you say ADDR like this, the old values will be still there. 0 to 99 will be intact. Then 100 to 199 will be available for you to extend. Okay. Then there is a size operator. So you can find out what is the size. Okay. In this example, ADDR dot size. Then you can delete the entire array. Okay. So here we had declared an array called AB, which is an array of integers. We had we had allocated storage for capital N integers, but at some stage we don't want it anymore. We can go and delete it. And see, when they write a language reference manual, they give a lot of what all is okay, what all is not okay, etc. So a lot of detail will be there. You don't have to go into all these gory details. If you know what dynamic arrays are. Okay. We'll try to use the dynamic array in one of our exercises. Okay. But I hope everybody understood what a dynamic array is. It is simply an array whose size we don't know at this point of time. Okay. And we can use new to allocate storage for it. Okay. And you can delete it when you don't want. So the reason why they would have given this is sometimes if you don't know the size of the array, then people sometimes declare a very large array, making it very inefficient. So therefore, it's better to allocate on the fly. Okay. Then in the same way, there is one queue. There is an associative array and queue. Here. So the difference between an associative array and queue, here it looks a lot like this dynamic array, except you have to put a dollar here. That is how you distinguish. So if you see a dollar, then you have to say Q1 is a queue of bytes. Names is a queue of strings. Capital Q is a queue of integers. Right? You can also specify the maximum value. You can say that it is a queue, but I will not allow more than 256 elements. Okay. So they have given this notation for it. A dollar colon 254. So a queue can be initialized. You can add values to it. Then you can access the zeroth element. If you say dollar, it will access the rightmost element. Okay. So if you say Q0, you will get 2. If you say Q dollar, you will get 8. And you can change the value. And you can add 6 at the end. So if you say Q comma 6, so all these values will be added here and then 6 will be added. Similarly here, Q is at the end and E is getting added in the beginning. Okay. So you can sort of grow the queue either from the right side or from the left side. And then they have also given things like push, pop, etc. Okay. So you can find the size of the queue at any point of time. Then you can insert anywhere you want. Okay. You can say at the position I insert E. And then you can delete an element. You can pop from the front, you can pop from the back, you can push from the front, you can push from the back. So the queue can be used in some situations. Remember, none of these are meant for synthesis. Okay. Sometimes people have asked me, will Verilog be able to synthesize all this? That is not true. These are all just meant for verification purpose only. They have provided these things to make life easier for the people who do the verification. Right? If you didn't have all these simple things like strings or dynamic arrays, queues, etc., your writing the verification test bench can be somewhat difficult. Okay. So here is so suppose we have to let us do is BCD again. Okay, we have done it before. So it takes as input, let us say BCD in number in and is BCD is output. And input logic 3:0 in and output logic is BCD. So we can write always at start if num in is greater than 9, then is BCD is false. Else,
Sir, can the port name be same as that of the module name?
huh? No, you have to change it. You have to make it is BCD as well. So you have to change. Now I want to test this guy. Okay. So let us try to use a queue or something like that or a dynamic array. So is BCD test. So let us build a queue maybe. Num is logic 3:0 num. So it is a queue. Okay. And we can I claim this works, but I don't know. Let us try. Let us see if this works. Sometimes I have had difficulties. Then maybe an int type. Then we'll need maybe logic equivalent 0 um, um, logic is basically out. Hmm. And is BCD out, is BCD, we can say is BCD instance, num in is BCD out. So we have just created a simple case, right? Now, in the initial part, what we'll do is for I equal to 0, I less than num dot size. See, num dot size will tell me how big it is. So that is one advantage of using this. You don't have to count and see how many there are. And then I plus plus. We can take num of I and assign it to num. And then wait for 1 unit of time. And then say dot display num equals percentage e is BCD equals percentage e. So num is num in and BCD is BCD out. So let us give it a try. So 9, 10, 5, 2, 3, 10, 4. Okay. So it has tested it. So I used it to store all the tests. Earlier, we did not have a way to do this. Okay, we are generating random tests, etc. But maybe I have created certain deterministic tests for which I know the answers. So I may even know the answers. This is true, this is false, this is true, 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 false. So 10 is repeated. False. Did I do it right? I mean, so these are my answers, which I have possibly used whatever other means to figure out. Okay. Then we could also write if answers of I is not equal to is BCD out, okay, then give this error. Okay. So here this time I don't expect any output. Okay, but, because this should be correct. Is it clear where this Q may be useful? You may find other clever ways of using the Q. Okay. You can also add, you can say num dot push back maybe 13. And num dot push front, maybe 15. Okay. So this time it will add those two, but the answers we had to answers, but so we also had to add the answers. Answers dot pushback is false, and answers dot push push front is also. Okay. So something like this. Okay. Similarly, you can try using all the others, like push. There is no great. Let me give this also to you. Is it making sense, everybody? Yeah, dollar is required, man. Why do you say dollar is not required? If I don't put the dollar, it becomes a dynamic array, right? See, if I don't put the dollar, right, then I can't do this. If I don't put the dollar, I can't do this. Then what I'll have to do is I can't do this either. I can't do this either. What I'll have to do is something like num equals new. Maybe I'll create 10 test cases. Then here you can say num dot size may also work. But unfortunately now I don't have any num I to write. We have to first initialize that guy. The
Sir,
rest is same.
other than uniform distribution, is there any other random option?
Yes, yes, yes. There are many. So you could, this is an alternate way. Okay, this did the same thing. Okay? But wait a minute. There's something wrong here. This answers and
0 to
I
50.
don't even have it, right?
Could be 0 to
Let's
50.
see. Hmm. Now answers of I. That also had to. Both will be initialized to 10. Then answers of I will be if num of I is greater than 9, then it is false, otherwise it's true. Okay. I'm surprised that I didn't get any errors.
Sir, it should be 0 to 15 in view random.
0 to 15. That is why I'm not getting any. 13, there is a syntax error. Okay. So this time we have checked it already. So we can, if I don't have this, let us see what it will do. See, the problem with this random range is it repeats. See, 3 got repeated, 8 got repeated, and so on. Whereas in the queue, we could initialize ourselves. So let me give you this also. So this is a dynamic array. Is that clear to people? Am I making sense? What about the others? Any doubts in whatever we discussed today? Then they have provided an associative array. Okay, that may be Q can be defined anywhere means what? It is meant for test benches. So it should be defined in test benches. So associative arrays are same as your dictionaries. Okay. So
So what is the way to know which constructs are available in Verilog and which are only available in System Verilog? How do we know this?
Verilog has very few. I told you, right? Int is there, then real is there. I'm sorry, integer is there, real is there, and then I think enumerated was also there in Verilog. Okay? And then all these things are new, short, int, etc. Okay. Reg and wire were there. So reg, wire, integer, real, enumerated. To my knowledge, that's about all. Okay.
Okay, sir.
Other than that, everything else is new. Verilog, pure Verilog is now nobody uses. Okay. See, most people have moved to system Verilog and UVM for verification. So Verilog is mainly for those who write RTL code. For them, Verilog is required. So for verification, nobody will use. I'm trying to find where it begins. Here it is. So if you say something like this, array B is an associative array. It takes a key which is a 21-bit key, and it gives you a string. So this is how generally people use it. So here is another one, an array name. I mean, the name of the array is array name, and it takes a key as a string, and it gives an integer. So let me see if I can illustrate it to you in some example. Let us create a module called test, right? And we'll define an array, an associative array, which takes as input a byte, and it generates square of that byte. So the input is a byte, and the output is maybe a short. So we want to store the squares directly. Okay, we don't want to compute the square. Square may not be such a great example, but we'll go it anyway. We'll say initial int or y. For I equal to 0, I less than, let us say, 100, I plus plus. So square of I equals I times I. This means when the key is 0, the value is I square. When the key is I, the value is I square. So we are associating the value. For example, if I is 3, the value is 9. When I is 4, the value is 16. So then later I can say square of, let me create some random numbers. So let me create int j. J is $u random range. Let us say 0 to 99. Then you can say display j equals percentage d, and square of j equals percentage something like this. Well, this unfortunately this guy may not support here. Like use cadence. So the iCal's Verilog doesn't support. So 65 square, 30 square, etc. Okay. So this is like a lookup table. Okay, we are storing the values ahead of time and we are using them. So square may not be something that we like to store, but if it is something else like sine or something like that, it may make sense to store. Okay, if you want to do that, you'll have to use real or short real or something. And it can be sine. And let us say by it may be. Oh, percentage F, sorry, percentage F will be displayed as percentage F. So these numbers are taken to be radians. Okay. So if you want them to be degrees, you'll have to convert. So these are some, I don't know whether, so this is a sine tape. So this is another useful data structure provided in system window. Okay, so let me also add this to your list. Making sense?
So what does the keyword byte stands for here, sir?
Anything else? So these are the basic data types. So if you go back to the beginning, we already saw all this, right? Most of these we saw. I have not discussed the event data type. Yeah, I need to discuss that. Then we already know that you can do your type def, etc. Then enumeration we have seen. Structures I have told you. Unions are very similar to C. Okay. And you can cast one data type as another data type. Void is also available. At this point, I don't want to discuss C handle. Okay. Let us look at event. This is useful. So you can create, see, this pause edge is an event, right? Pause edge of clock, like edge of clock, right? So those are all already defined for you, right? So we are able to say always at pause edge of clock, things like that. In the same way, sometimes you may want to create your own events. An example could be in our, we had the BCD adder, right? In the BCD adder, in the BCD adder, I explained to you that we add 6 in two situations. One is when the sum becomes more than 9, right? Or when we get a carry. See, maybe we want to distinguish between the two. If the carry becomes 1, for me it's an event. Okay? If the sum becomes more than 9, then it's an event for me, right? So I can declare these as events, and maybe in the test bench I can check if this event has occurred, then increment some counter. So when I do some testing, right, I may want to get some confidence on what are the, have I reached certain corner cases? Okay. In this example, the uh, carry becoming a 1 is important for me. Then the sum becoming something in the range 10 to 15 is important for me. And I also want to know when uh, you know, the carry is 0. Maybe it helps me to get some idea of what is the coverage. Okay, how well have I covered all the. So I may want to create events and create counters and say when I simulated 25 times, out of them 10 times the output was correct 0 to 9 and the carry was 0. And in maybe 5 cases we had carry equal to 1. And in the remaining cases, the sum was more than 9 or something like that. So if you want to classify your tests, you may have to create these events. Unfortunately, he has not given more details here, but there is a way to set the event. You can say uh, done. You can give a right arrow and say you can create an event. So maybe he has explained it later. We already know that this add syntax is used to check. And we can say p check for this event called p dot status. What in the syntax? I don't recall that how to assert this in. Tomorrow I'll be able to give you. I'll look up and I'll tell you. I'll give you an example of event edit. So we'll do the same exercise tomorrow, right? I thought it is here and I confidently assumed that it is there.
Are you getting this point? The best point of this particular program.
Yeah, I think that's fine. To trigger an event, you have to do like this. You can say trigger. You can wait for 1 minute of time and trigger. So what it
Sir, I
means
think
is,
sharing. Sir, I think sharing is not there.
oh, sharing is not there. No. Something happened, no? Suddenly something changed.
I think suddenly something happened.
Now you can see. Okay.
Yes, it is visible.
Yes, sir.
See, if you have defined done and blast as two events, right? Um, the way to trigger an event is like this syntax. You can wait for an event to occur, right? And this is also another way to wait for an event. We'll have to think of how to use this event in a useful way. See, one suggestion I can give you is, yesterday we were discussing a triangular waveform, right? See, the triangular waveform was supposed to generate something like this. So it was supposed to generate 0, 1, 2 up to 7, then 6, 5, 4 to 0. Now, how were we verifying it? We were only looking at the output, the dollar display outputs we were looking at, right? But imagine this was a more complex sequence. So maybe we have a situation like maybe there is possibly some sort of a memory, okay, and we want to know when the uh, there may be an address that is being given to this memory, right? See, we may want to know if this address becomes an invalid address or something like that. That means it is going out of the bound. Or there may be a cache, with this memory. The event could be a hit or a miss, meaning the page that we are looking for is in the cache or not in the cache. Okay. So that is called the hit or miss. So maybe when we simulate, we want to know how often we have a hit and how often we have a miss. So event may be a good way to, sort of count that. Sometimes, there may be a relation between some signals. Okay. So maybe there is some signal and that causes maybe some other signal to go high, etc. And if you see this pattern, it may mean something for you. It may trigger some action. So you may want to watch several events and see whether a particular sequence of events is occurring. Okay. Such as maybe you are worried that maybe there is a cache which is being shared by many maybe processes. There may be many processes which are sharing the cache. So maybe there are events like both of them are trying to get to the same page, right? So maybe you are worried about some situation like maybe you have created a deadlock situation somewhere, or maybe you have declared maybe there is an error in the implementation because of which stale data is being read by some other processor. So there may be so many situations like that. So Verilog, system Verilog allows you to define these events, etc., and sort of wait for such events. Or whenever those events occur, you can increment some sort of a counter or something and display them as performance parameters. So when we propose some new algorithm, okay, maybe a shared cache or something like that, okay, then the the data pattern, the simulation pattern um, may result in certain events, okay, and we may be interested in watching for those events. So I will discuss that a little bit more in tomorrow's class because we don't have that much time today to cover it in detail. Okay, so in tomorrow's class we'll discuss that event thing in more detail. Okay. Is there anything that we did today that is not clear? We still have a few minutes. We have about 10-15 minutes. Okay. So to summarize, what all have we done? We have looked at S3 data types. Okay. Today we looked at, I think, the queue. Then we looked at, what is it? Dynamic array. We have also discussed the multi-dimensional array earlier. Then these are static arrays. It means the allocation is done once and for all. Whereas dynamic array, we do it on the fly. Then I would have mentioned to you packed and unpacked arrays. Then, of course, users can define type def, struct, etc. Then event, I'm sorry, immune was there, and I think event also we talked. Yes. I have given examples of queues. String also is there. String is another. So we have strings, associative arrays also. So queues, dynamic arrays, associative arrays, multidimensional arrays, strings. Then in addition to all this, they also have class. Okay, so we haven't discussed that yet. We will also have classes. So it's a pretty large language. It has a lot of different constructs, and this one is not supported in ICARS very well. I think the others are supported. So we'll tomorrow, when we meet, I think they are announcing already that it is tomorrow is 12 o'clock. Okay, so you can get some rest, and in the morning, if you find time, go ahead and try some exercises. So you can try, just like the BCD adder, try if you can create a, n-bit adder subtract. When n is large, okay, suppose you wanted to do a 64-bit adder, right? Then you can't design it as a ripple carry adder. Okay, so you'll have to try the method I discussed today. Some similar method you have to try. So try design a 4-bit full adder subtractor. Use it to add 264-bit ones. Verify for test cases. So you cannot exhaustively test it. Impossible, right? It's a 64-bit adder. The number of test cases will blow up, right? So you will have to only try a few test cases, maybe 100 or something like that. So this can be an exercise for you. And try to see, you can try use as many data types of SV as possible. I think I forgot logic, etc. I think these are also there. Logic, byte, etc. Yeah, you can try look ahead, carry look ahead. And you can, that will be nice. If you can design a carry look ahead adder, right? That will be nice. So give it a try. Any other questions before we break? Let me look at the participants. Okay. Any doubts? Dr. Manjula, Dr. Jalaja, Dr. Shiju, Dr. Vinda, Dr. Kavita, Dr. Leela. Any questions? Another exercise you could try is see this so pace is high. Okay. You see, there is a try this exercise also. Imagine that there is a memory, okay, which has been divided into many pages. Assume that there are maybe 63 pages, 0 to 63, 64 pages. And then there is a cache which has 8 pages. So the cache can only accommodate 8 of these. We don't have enough space. So at any point of time, we can only keep 4 of these pages. So the pages here are numbered. So initially, let us say we have decided to load pages 0, 1, 2, and 3. Assume that it is fully associative cache. That means any page can be loaded anywhere. If 0 is loaded here, 1 is loaded here, 2 is loaded here, and 3 is loaded here. 3 is loaded. Actually, there are 7, right? So we have 7, 4, 5, 6, 7. So we have loaded these pages to start with. Then when the users start using the CPU, it is possible that the accesses may not always restrict themselves to 0 to 7. So we may access page number 0, again page number 0, page number 1, page number 2, page number 1, page number 3, page number 4. Then there may be an access to page number 8. Okay, this page is not there in the cache. Okay, so we have to bring it back. We have to bring it from the memory. So this is called as a miss. These were all hits because we already had these pages. So when a miss occurs, we will have to remove one existing page. So we can use what is called as least recently used algorithm. See, the page 4 has been recently used. So the age of page 4 is just 1. The age of page 3 is 2 because it has just been used a little bit before. Then age of page 1 is 3. Age of page 2 is 4. Age of page 0 is 5. On the other hand, 6 and 7, their ages are 6 and 7. We have not used 6 or 7. So these are candidates for removal. We can remove any one of them. Okay. So the hardware must do the following. It has to check if requested page is in the memory, in the cache. Right? And if it is there, then well and good, right? If it is not there, you have to decide which page to eliminate. Decide which page in cache must be replaced. Isn't right? Okay. So try to see how much you can get far. The idea is for you to think and come up with some sort of a design, something, right? And then you can see that verifying this is not going to be so easy. Meaning whether really LRU is being followed or not. Okay? Maybe there is a bug in the algorithm because of which least recently used policy is incorrectly implemented. So the verification hardware, or I'm sorry, verification has to check whether Um, in addition to that, you may have to keep a bit called valid. Okay, see these initially all of them are valid, valid, because we have loaded pages, good pages. Okay? Um, Later, when we remove pages, they may become invalid. Okay, for example, when we update a page, suppose we are trying to write to the memory, right? Then there are two policies that we use. One is called as write through, and another is called as write back. So write through means it will update both the cache and the main memory, whereas write back means it will update only the cache. So if you are using write back, then if you have updated the cache, it is what we call as there is a bit called as the dirty bit. Okay, so we have to keep track of that, and when we replace, when we decide to replace that particular cache page, then we have to write that page back to memory. So there are many such things that you have to take care of when you design a cache controller. So I want you to think about a cache controller. Keep the memory simple, only 64 um, pages. And see, because you are using 64 pages, assume that each page has maybe 1024 locations. Okay, so the whole system is 64K. There are 64 pages, each of 1K. So the memory is only 64K, and the cache is only 8K. So we will have to have a tag to find out which page in the main memory is actually currently loaded in the cache. Okay. So we'll have to use tag memory, and then we have to search through the tag memory to see whether the requested page is in the cache or not. And if it is not there, we say it's a miss, and we have to go and load that page. Whereas if it is there, um, I'm sorry, when we load, we have to decide which one has to be replaced. And before we replace it, if it is been updated and we are doing write back policy, we have to write that page into the main. So many things like this will have to happen. Okay? So please check how you will. Please think about how you will design this, right? think about how you will verify an implementation. You may not be the one who implemented it. Somebody else implemented it. So you have to think of the okay. So think. All right. So good. I will see you tomorrow then. 12 o'clock.
Thank you very much, sir.
All right. Thank you. Bye. Good night.
Dear participant, tomorrow we are meeting. Tomorrow is a weekend, Saturday, and we'll be meeting at 12 in the noon. So please join 15 minutes before.